Yeah, I hope you guys are able to see the screen which is being shared. I'm sharing my blackboard now. Yeah, I hope it is visible to all of you,
Yes, sir.
right? Yeah. Okay, great. So last class, we have looked at alternating current chapter, and we had a complete lecture where we devoted time to understand what are the different concepts involved in it. So now, and we had also done few questions. I think roughly three or four questions we had solved. So now we will see some more questions, different models, and then before we move on to the next topic. Okay. So here is a question on the screen. So I already wrote it, and kept it ready. So you can see that there is a series LCR circuit where your inductor is 1 Henry and capacitor is 20 microfarad and a resistor of 300 ohms. They all of them are connected together in series to an AC source having source voltage 50 volts and frequency 50 upon pi hertz. Okay, so you will have to calculate what is the impedance of this circuit. So again, if you guys can have a quick, recapitulation of the formula, you can try this and you can tell me what would be the answer for the impedance. Okay, before we solve it, I'll give you the options anyway, so you can start solving it. So let me write the options in that time. So option A is 200 ohms, option B is 100, and option C is 300, and option D is 500. Okay, these are the options. So you have to tell me what is the value of impedance that is given for this question. Yeah. So what is the formula, children, we generally use to solve this question for a series LCR circuit? So how do we calculate the impedance when you have three different components, that is inductor, capacitor, and resistor, when they are connected in series? So how can we calculate the impedance? It is given by the letter Z. I hope you guys remember the formula. It's under root of, I hope you guys remember, R squared plus, is it XC minus XL or XL minus XC?
XL minus XC.
Yeah, so XL minus XC the whole square. Okay, so you need to substitute in this formula and then find out. R is anyway there as 300, but then when it comes to XL minus XC, you will have to go and you will have to calculate the values. Okay, so XL is nothing but your inductive reactance, XC is capacitive reactance, which have their appropriate formulas. So you will have to substitute them there and then find out. So how is XL related? Anybody? How can we calculate XL or inductive reactance? It's given by,
Omega, sir.
yeah, it is given by omega L. That's right. Same way. What is XC?
1 by omega c, sir.
Yeah, it is 1 upon omega C. So you go here and you substitute, children. Okay, omega we can calculate, right? How do we calculate omega?
Sir, 2 pi into 50 by pi, sir.
Yeah, 2 pi f L. So f is 50 upon pi. You just go for a substitution. So 2 pi times 50 upon pi times L, which is 1 Henry. Okay, so just put 1 there. What is the value that you get? So you get 50 twos are 100, right? 100 ohms. What about XC? What is the value that you're getting? Same way you will do it. So 1 upon 2 pi times 50 upon pi times C, which is 20 microfarad. So 20 into 10 power minus 6. So you need to go for a simplification. So again, I think your pi is getting cancelled off. How much are you getting? 1 upon omega C value, you will have to go for a simplification. How much is that? Are you guys getting 500?
Yes, sir.
Getting 500? Okay, then now you go and substitute it. You go for substitution and then go for a simplification. So what's the final result? It's an easy one.
300 ohms, sir.
Yeah. Okay. So you go for a substitution and then you finally simplify. You will get the answer as 300. Are you sure? It's 300. 300 square plus how much is the value after you subtract?
500, sir.
I think it should be 500, right? Not 300 because I'm getting 500. Okay, so you will be getting the answer as 500. Okay, so you substitute it and then simplify it properly. You get the answer as 500 ohms. Okay, so the answer is 500 ohms, which is option B in this case. Okay, so here, children, main aspect is you will have to identify what is the nature of the circuit given, and you just go for a substitution. Okay, so identify it, then go for a substitution. So this one was a simple one. Okay, to begin with. So we'll go to the next type, the next model. Now we'll see a different one.
Manish, can I interrupt here a little bit?
Yeah. Sure,
இந்த
continue.
எலக்ட்ரிக்கல் கொஸ்டின்ஸ் எல்லாமே அஃப்கோர்ஸ் எனக்கு ஈஸியாக தெரியுது,
Hmm.
உங்களுக்கு ரொம்ப ஈஸியாக தெரியும். நம்ம குழந்தைகளுக்கு கொஞ்சம் போடும்போது என்னன்னு தெரில, அவங்க கொஞ்சம் கான்ஃபிடென்ட்,
Okay.
தேர் லேக்கிங் கான்ஃபிடென்ஸு.
Okay.
நாட் திஸ் பர்டிகுலர் கொஸ்டின், இன் ஜென்ரல்.
Ah,
குழந்தைகளா
okay.
நீங்கள் கேளுங்க. ஏன்னா லாஸ்ட் டைம் நீங்கள் வர்றதுக்கு முன்னாடி ஒரு 3-4 கொஸ்டின் போட்டோம் இல்லையா, அதில் ஒரு கொஸ்டின்
Ah,
எலக்ட்ரிக்கல் கொஸ்டின், அது அவங்க ஈஸியாக இருந்தால் இருந்த மாதிரி எனக்கு தோணுச்சு. பட் அவங்களுக்கு அது
okay.
கொஞ்சம் ஏதோ கன்ஃபியூஷன் இருக்குது. அதனால் நீங்கள் அந்த if it's possible, you can know,
Hmm.
give them explanation of resistor, capacitor and inductance, அப்புறம் வோல்ட்னு என்ன, ஆம்பியர்னு என்ன, பவர் how it is related. இப்போ இல்லை, when there is
Hmm.
any relevant question you can give some explanation also. ஏன்னா
Sure,
அதில்
Uncle,
ஐ திங்க்
definitely.
கன்ஃபியூஷன் இருக்குது. அது எனக்கு நாங்கள் படிக்கும்போது எனக்கு அந்த கன்ஃபியூஷன்லாம் இருந்தது. மேபி அது
Okay.
சிமிலர் கன்ஃபியூஷன் அகெயின் ஐ திங்க் தே ஆர் ஃபேஸிங். அந்த ஏஜுக்கு அது கொஞ்சம் டைஜஸ்ட் பண்ணுறது கஷ்டமாக இருக்கும்னு நினைக்கிறேன். நீங்கள் இஃப் யூ
Okay.
கேன் ஸ்பெண்ட் சம் டைம் 5 minutes
Kandippa,
எக்ஸ்ட்ரா
definitely.
டு கிவ் தட்
Definitely.
கிளாரிட்டி ஆஃப் தட். இப்போ இப்போ
Yeah.
பார்த்தீங்கன்னா கெப்பாசிட்டி எதுக்குன்னா அது வந்து பவர் சார்ஜு சார்ஜிங்க்கு யூஸ் ஆகுது அந்த மாதிரி. அப்போது
Hmm.
when they know the application of these element, ரெசிஸ்டர், கெப்பாசிட்டர், இண்டக்டர், அப்போ ஈஸியாக இன்னும் கொஞ்சம் அவங்க அண்டர்ஸ்டாண்ட் பண்ணுவாங்கன்னு நினைக்கிறேன்.
Okay. Sure, Uncle. You will
அது
definitely
கொஞ்சம்
incorporate.
பார்த்துங்க.
Kandippa. Yeah. Okay. So let's move to the next model. So here, basically, this is also, electricity related questions only, as sir rightly said. So you can definitely interrupt and you can ask. So anywhere if you're facing any difficulties. So please don't feel shy. Okay. And I will also explain it. Okay. So we are going from scratch. Do not worry. So concepts may be at a higher level, but again, we'll pitch in from the basics and then we will move on. Okay, sure. So that definitely that is being taken care of. So we'll go to the next type of question. Now, certain questions will have circuits. Certain questions might not have circuits. So they would just put it in a statement form, and then they ask you, to draw the circuit. Real time, you will be drawing the circuit, and then you will have to solve it and then get the answer. So there are many aspects of questions being asked in the form of statement where you understand the statement and then you draw the circuit on your own, then you solve and then find out the answer. So there are two different approaches to competitive exams where questions can be asked, wherein the circuit can be given ready-made and you will be solving it and giving the answers. Second, the statement can be given and you will have to, based on analyzing the statement, you will draw the circuit and then you will simplify. So we will look at both aspects. Wherein here this question the circuit was given, so sometimes circuit might not be given. So wherein you will have to draw the circuit on your own. Okay. So we will look at all the aspects today. Don't worry. Yeah. So now we are moving on to the next type, next model of question. So let's see it. Yeah. So here comes the next question. So a transformer, let me just write it down. A transformer is used to reduce is used to reduce the mains supply from 220 volts, okay, to 11 volts. Okay, full stop. Say if the current in the primary if current in the primary and secondary coils are 5 ampere and 90 amperes respectively. Okay, the efficiency of the transformer is, so again we have options here. Okay, I'll give you the options and then I'll explain the question. So it's an easier one. But we again you need to interpret the data from what is given. So option A is 90%. Option B you have 75%, and option C 40%, and option D 60%. Okay, so this is what they have given in this particular question. You have a transformer, and this transformer is used to reduce the voltage. They are telling so from 220 volts it is being used to reduce the voltage, okay, to 11 volts as you can see, and they've given you the currents in the primary and the secondary. So this is what they have given. Now when you have questions like these, now first step, as I told, try to convert this into an illustratable form. Try to illustrate the question. Okay, so let's try to illustrate. Here transformer is used to reduce. They are telling the supply voltage is being reduced. You can see here it has been reduced from 220 to so called 11, right? So voltage is being reduced. So what is the type of transformer that is being used here? Okay, that is what we need to think about. Okay, any guesses? What would be the type of transformer that is implemented here to achieve
Transformer.
this? Yeah, it is a step down transformer. Why we call it step down? Because it is stepping down the voltage or it is reducing the voltage. That is the meaning. Okay, so here the type of transformer used is step down. So I will write it here. So the type is step down transformer. Okay, so a step down transformer is always used to reduce the voltage. Okay, so that is the reason a step down transformer is used. Try to draw the transformer, or let's try to illustrate the transformer using a simple circuit. How do we do that? So first you take an AC main source. To the AC main source I am going to connect the coil. We have two different types of coils in the transformer. If you guys can recall, we have learned we have something called as a primary coil, and we also have something called as a secondary coil. Now, what is a primary coil? Right? The coil that is being connected to the AC source or to your supply voltage. You call that as the primary coil. Okay, so here this is connected to the coil that I have drawn here is connected to your AC source. So let me show it. So AC source, my AC source frequency, I mean voltage is given there in the question 220 volts because it is reducing, right? So you are supplying 220, no doubt, but the output is 11. So here 220 volts. So I'm writing the voltage there as 220. Done. Now here you have a primary coil. Now primary coil, they have given you one more information. The primary coil current is also given in the question as 5 amperes. All right. So I will write next to the primary coil the current as 5 amperes. So here current is 5 amperes. So I'm just writing it there, or you can also put the symbol for primary current and write it. Okay. So primary current, we can write it as IP. That is the symbol current in the primary, which is 5 amperes. So we are showing that. Okay. Now after this, you have another coil that is called the secondary coil. Okay, so there is another coil. Okay, so I'm just doing a freehand drawing. Put up with me. So here there is another coil next to it, which is called your secondary coil. So this is your secondary coil, and they have given you that the current in the secondary is 90 amperes. That is also specified in the question. So IS is equal to 90 amperes. Okay, that is also given, children, in the question. Okay, so these are the data that we have in the question as of now. 90 amperes. One more data is also given. What is that? They're telling you that voltage is reduced from 220 to 11 volts. So that means voltage across the secondary is also given. So 220 is nothing but primary voltage. So we can write it as VP. Now I'm writing it as VS as the secondary voltage, which is 11 volts. That also I'm writing. So now when you try to depict the question like this, now it is easy for us also to understand what is the given data. And then when you illustrate, things become much more clear. And now we can calculate so-called the efficiency of the transformer. So what is the formula for the efficiency of the transformer? Okay, so it is given by the symbol eta, where eta represents the efficiency. So very simple, it is output power upon input power. The ratio of output to input power times 100 is basically the efficiency. Okay. Now, what is output power? Output is something that you get. Input is something that you supply, right? So here, what are we supplying? We are supplying a voltage of 220 volts, and the current of 5 amperes is being supplied by us. All right. But output is something that the transformer is giving you. After you supply, it is giving you, the output. That is which with respect to the secondary. Secondary current we have it as 90 amperes, and secondary voltage you can see is it is reduced to 11 volts. So that is the output part. So secondary whatever values you have that pertains to the output, and the primary whatever values you have corresponding to the primary coil, you call it as all the primary data. Okay, so that is the input. Now we will go and substitute the values. So here efficiency is equal to as output power. What is the formula for power? We have already learned the formula. It is the product of
Yeah, yes,
potential,
sir.
yeah, potential and current, V into I, right? We can call it as V into I, no doubt. When I say output, output I told you it is with respect to secondary. So I can write it as Vs into Is upon input. Input power is nothing but what is being supplied. So supply voltage, which is primary voltage, times primary current, which is I, into 100. Simple. Now you go and substitute the values that you have. Okay, go for a substitution. Whatever the values that we are having, we have secondary voltage, we have secondary current, we have primary voltage, we also have primary current. Okay, so we just need to go and substitute the values now. Okay, so when you substitute it, you will get the answer. So voltage, secondary voltage is 11 times secondary current is 90. So 11 times 90 upon primary voltage. Primary voltage is 220 times primary current is 5 amperes. So let me cancel out the zeros. 11 ones are 11 twos are 22, right? And then go and cancel it out with 2 fives are 10 anyways, right? So I carried as 9 upon 10 into 100, right? So how much is the value that's coming out? 10 also you can cancel out, 1 0. So you're getting the answer as 90. Are you guys getting the answer as 90%? So 90% is
Yes,
basically
sir.
the efficiency of this transformers. That's it. So when you have a question like this, try to illustrate it. You draw the circuit and then you try to interpret the data. That is very, very important. First thing is understanding the question, draw the circuit and interpret the data from it, and then you go for solving. Okay, you will get the answer. So here the answer is option A, which is 90%. So the efficiency of this step down transformer is 90%. Okay, so that's how you solve this type of questions, wherein you have the data, you interpret the data, and then you go for solving it. All right, so that's how you do this. Now we'll move on to the next one. I hope this question is clear to all of you. So now we'll move on to the next type. Moving on to the next model of question. Okay, different way how questions can be asked. So another model is there. So mostly alternating current chapter. The questions I'll tell you. most probable areas are series LCR circuit, LC oscillations, and when your capacitor and resistor is connected, inductor and resistor being connected, and then all three of them, that is inductor, capacitor, and resistor being connected in series with an AC source. So impedance of all three is important, and then efficiency of transformer, and coming to the transformation ratio. So these are the areas from where questions are typically asked. Okay, so these are the important areas from where, or we can say most probable areas from where questions are generally asked. So let's go to the next type of question. Okay, an LC circuit contains 40 millihenry, okay, inductor, 40 millihenry inductor, and 25 microfarad capacitor. Okay, assuming assuming the resistance of the circuit to be negligible, to be negligible, the time, okay, the time is measured from the instant the circuit is closed. Okay, from the instant the circuit is closed. Now, the energy stored in the circuit is completely magnetic at times, that is in milliseconds. So, if the energy stored in the circuit is being completely magnetic in milliseconds, so you will have to interpret the values. So the options I'll give you. Option A, 0, 3.14, 6.28. Option B, 0, 1.57, 4.71. Option C, 1.57, 4.71, 7.85. And option D, 1.57, 3.14, 4.71. So like this, you have 4 options. So first read the question. So once you read the question, we'll try to interpret what is the data. So same procedure you would follow. Okay. And then we try to answer this question. So here you have an LC circuit which is containing two important components. What are they? You can see that there is an inductor and there is a capacitor, no doubt. And they're telling you the resistance. You're assuming the resistance of the circuit to be negligible. That means you need not consider the resistance. So the time is being measured from the instant the circuit is closed. That means when the switch is on, that is the meaning. Okay. So what is the energy stored in the circuit? Completely going to be magnetic for all the components. So you will have to consider. Okay, so that is when you calculate what is the energy stored. All right. So first, for this circuit, now given data, let us first try to write it. What is the given data? First, the given data is you have inductor. So inductor is equal to 40 millihenry, okay, which is equal to 40 times 10 raised to minus 3. I hope you guys know how to convert, right? 40 times 10 raised to minus 3 Henry. Done. So that is inductor. Same way, capacitor value 25 microfarad, right? So 25 microfarad, you can write it as 25 into 10 power minus 6 farad. So you express everything in terms of their appropriate units, power of 10. Okay, so these two things are given. Apart from that, now when you have this particular value, so first try to find out, we are trying to find out what is the time period, very important. Now, whenever you have time period, we all know what is time period, children, relationship between time period. Can anybody try? Because here we wanted time, right? So whenever they say time period, you try to correlate what is the formula that binds time period and the data that we have. The data that we have is no doubt inductor and capacitor. But don't you think there is something called as a frequency that is involved? Isn't it? So the frequency of LC oscillations or inductor and capacitor together is what you are going to apply here. Okay. So frequency for LC circuits is given by 1 upon 2 pi under root LC. So this is the formula that we need to use to find out the frequency. Okay. So you use this and you will calculate the frequency. Once you have frequency, you can calculate time period, isn't it? So what is the value for this? If you go for simplification, in terms of pi itself, you can keep the answer, and then you can multiply the pi if needed. So go for a simplification. It's 1 upon 2 pi under root. So L into C. So I'm substituting all the values. So 40 into 25 into 10 raised to minus 9. If I simplify this, I will be getting 10 power minus 3 coming up 10 power 3 upon 2 pi. Right? You will get 10 power 3 upon 2 pi hertz as the frequency. This is what you will get when you go for simplification. Okay. So, the 2 pi I'm not disturbing as of now. I'm keeping it as 2 pi itself. Okay. Now, time period. How is time period related to frequency? Everybody knows. So, time period is represented as the reciprocal of frequency, right? So, 1 upon f. So, what will be the answer? So, it is nothing but 2 pi upon 10 power 3 seconds. 2 pi upon 10 power 3 seconds. So, how can we write this, children? Can I write it as 2 pi milliseconds? Because 10 power minus 3, no? If you bring the 10 power 3 up, it becomes 10 power minus 3. So, the time period is simply T is equal to 2 pi milliseconds. MS is nothing but millisecond. So, that is the time period for this corresponding LC oscillation circuit. Now, we have calculated the time period from the frequency of the given circuit and we have got the data. So we have got the time period, no doubt. Now the question is based on the energy stored. So here there is a small twist. Based on energy stored, if they are asking you the time period, you need to understand that for energy stored for magnetic, the circuit to become completely magnetic is different, and energy stored for the circuit to become completely electric is also totally different. So there are different aspects to this question, so which we have to understand. The first aspect, energy stored when it is completely electrical, is what we will write first. Okay. So first one. So here three important concepts come into picture. I'm writing one by one. Energy stored. Okay. Energy stored is completely electrical. Okay. Is completely electrical at the times when t is equal to 0, comma t by 2, comma t comma 3t by 2, and so on. So these are the multiples. Energy stored is being completely electrical at these times. When it is 0, t by 2, t, 3t by 2, and so on and so forth. Okay, this is for electrical. Same way for magnetic. Okay, second one, energy stored is completely magnetic at times. Again, we have the relation for that time period as well. So when t is equal to t by 4, comma 3t by 4, comma 5t by 4, and so forth. So on and so forth. You can see it is odd multiples of t by 4 is what you can see here. So t by 4, 3t by 4, 5t by 4. So in that multiples of t by 4 is when the energy stored becomes energy which is stored is completely magnetic. So these are the relations for time period which you will have to keep it in mind. Okay. So having these two information in mind, now we have the time period with us. We go for a substitution. So what will be the first corresponding value when you go for a substitution? Because you have the time period. Let me just scroll up. We have found out the general time period as 2 pi milliseconds. Having that in mind, we would go and we would substitute. So first, it is t by 2, right? So go and when you substitute it there, so you will get it as t is equal to pi upon 2 milliseconds. Okay, so pi by 2 milliseconds. Then you have it as 3 pi by 2 milliseconds. Then 5 pi by 2 milliseconds. Now, I am only writing for completely magnetic. Why? Because in the question, they have clearly specified the time periods at, at which the circuit is completely magnetic. Okay, only we are interested about magnetic. So for magnetic, the formula that you would use is T by 4, 3T by 4, 5T by 4, so on and so forth. Wherein your T being 2 pi, you go and substitute the values, you will get the answer as pi by 2 milliseconds, 3 pi by 2 milliseconds, 5 pi by 2 milliseconds. So that is the answer. Now you will have to convert this to decimal because in the options are given in terms of decimals. So T is equal to pi by 2. So pi by 2 in terms of decimals, if you're going to write, the answer will be 1.57 milliseconds. 3 pi by 2, it is 4.71 milliseconds. 5 pi by 2, it would be 7.85 milliseconds. So these are the options. These are the answers. 1.57, 4.71, and 7.85. Okay. So the answer is option C. So like this, you will approach this question. Okay. I'm again repeating. Let me just explain it again. Okay. So whenever you have a question where they have given you the value of inductor and capacitor, and assuming that the resistance is negligible, they're asking you what are the time periods for the question where it is completely magnetic. First, you will find out what is the frequency using the formula 1 upon 2 pi under root LC. Then you will find out time period as the reciprocal of frequency. Finally, you will substitute in the relation for time period in terms of multiples for both electrical and magnetic. So for here we wanted only magnetic time periods, which are in odd multiples of t by 4, which is t by 4, 3t by 4, 5t by 4, so on and so forth. Okay, then you go for substitution, and then finally you would simplify and get the answers. Okay, so this is how you solve this question. I hope it is clear. Okay, this is it's a new model based on LC oscillations. Fine. This is how you approach these type of questions. Okay, I hope this part is also clear. Okay, this question is clear to all of you. Fine. Any doubts you can ask before we move on to the next type of question. All right. Okay. Fine. So let's go to the next model. One more model we will see, and then we'll move on to the next chapter, which is having a great weightage. So here there is another question. Yeah, here comes the question. So a DC voltage, okay, a DC voltage of 200 volts is applied to a coil of self-inductance, okay, of self-inductance 2 root 3 upon pi, okay, 2 root 3 upon pi Henry. Then a current of 1 ampere, a current of 1 ampere flows through it. Okay. Now next, by replacing DC source, by replacing DC source with an AC source, okay, of voltage 200 volts, the current the current is reduced the current is reduced by 0.5 amperes. Okay, it is getting reduced by 0.5 amperes. The frequency of the supply is, the frequency of the supply is, so they're asking you what is the frequency of the supply. I'm giving you the options. Option A, 100 hertz. Okay. Option B, 75 hertz. Option C, 60 hertz. And option D, 50 hertz. Okay. So these are the options. All right. So here in this question, they have given you first initially it is DC voltage. Okay, not AC here, it is DC. So a DC voltage of 200 volt is applied to a coil having self-inductance 2 root 3 upon pi Henry. So they're telling when DC voltage is applied to an inductor of 2 root 3 upon pi Henry, a current of 1 ampere is flowing. Then what are they doing? Then they are replacing the DC source with an AC source of same voltage, which is 200 volt. By doing so, the current is reduced to 0.5 amperes. It is getting reduced. Now, if this is the case, they are asking you what would be the frequency of the supply. Okay, so frequency of the supply voltage is what they are asking in this question. Okay, so we will have to find out what is the frequency of the supply. How do we approach this particular question? Where we don't have information about the impedance nor the resistance of the circuit, but we can still find out. There is an approach. There is a method to still find it out. How do we find out? So that is what you will have to identify. Yeah. Anybody would like to try? Even though the data is not given here, but still you can find out that data. How? How can we find out? Yeah, just give it a try. No?
I naught equal to V naught by omega L, sir.
I naught is equal to V naught by omega L. Okay.
From omega, we can calculate the frequencies.
Yes, from omega you can calculate. How much are you getting if you do that? Okay, so one of them is pi. So here, that is also, that is a general method, right? So I naught is equal to V naught by omega L. But here there are two cases. So you can do it only if one case is given. What you're telling is right, but that can be done if only one case is given. Here you're having two different cases. So first you will have to try to find out what is the resistance of the coil. So how do we calculate the resistance of the coil? Very simple. Try to apply the Ohm's law, right? So because initially they are saying it is DC source. Initially, so we don't have an AC source. Just you have a DC source. So initially you can apply Ohm's law. R is equal to V upon I. Use this and try to find out. So V is 200 volts. And initially I think current was given as 1 ampere, right? So 200 upon 1, which is 200 ohms. So directly 200 ohms. This is with DC source. Let me write it here. Okay. This is for DC. For DC source, this is the value. Okay. Same way, you go ahead and you try to find out with AC source. With AC source, what would happen in this situation? We want to find out what is the current. Yes, that's true. So current I is equal to, so say we have the relationship between current and resistance and all that. So we can write I is equal to V upon, no doubt. Here it is impedance. Whenever you say AC source, you will not use the word resistance. Please keep this in mind. So I is equal to V upon Z. This is what you will use, where Z is nothing but the impedance of the circuit. Is it clear? So it is the impedance. So I'm trying to use this relation. Now current, they have itself told. How do we know the current? In the question itself, it is mentioned. When you're replacing with AC source, okay, they're saying current is reduced to 0.5 amperes. So it is 0.5 amperes. So 0.5 ampere is equal to V. V is nothing but the voltage that is same. There is no change in it. That is 200 volts upon impedance. What is the impedance of the circuit? It is under root of R square plus XL square, right? Because you just have an inductor, right? So you would use this particular relationship. Okay. So when you use this particular relationship, so here we only wanted the inductance. Okay. We don't want inductive reactance as such, right? So we only need that particular data. So therefore, go for a rearrangement. 0.5 times root R square plus XL square is equal to 200. Now I want to remove the root. So what can I do if I want to remove the root? You need to square on both sides, right? So square on both sides. What do you get if you square on both the sides? Anybody? Go for squaring it and then go for simplifying it, right? So R square plus XL square is equal to, the 0.5 is nothing but 1 upon 2, right? So 1 by 2 I'm shifting to the right. It becomes 400. Are you guys able to understand? So it is 400 square. Okay, this is what I have done. Okay, so far so good. Now I'm going and substituting the values. Okay, so R square, I know that R square, R value we know it. We have calculated and kept anyways. So 200. So 200 square. Okay, R is 200. So 200 square plus XL. What is XL formula? Anybody? XL formula.
Omega L, sir.
Correct. Omega L. So omega L, the whole square is equal to 400 square. So omega L the whole square. Omega is nothing but 2 pi f, isn't it? So we know that. So that is 2 pi f. So we can write 2 pi f L the whole square is equal to, and we go for a simplification. Okay. And then you try to calculate it. So 2 pi fl. So here what we need, they are asking us only the frequency. And inductance value we already have here, which is 2 root 3 upon pi. I will go and substitute that value there. Okay. So 400 square minus 200 square, I think you guys know how to do that, isn't it? So 2 pi f is what we want to find out. Okay. L value is nothing but 2 root 3 upon 5, the whole square. Okay, is equal to, how much is 400 square minus 200 square? Go for a simplification. It is of the form a square minus b square, right? A plus b into a minus b. How much is that, children? 400 plus 200, which is 600, right? And 400 minus 200, which is 200. Okay, so I'm using identity and solving. And then 2 2s are 4. So 4 root 3 f the whole square is equal to 6 2s are 12.
1,20,000.
Yeah, 1,20,000. Now square term, I'm trying to bring everything out. I'm trying to square everything and then finding out what is f. So rearrange for f. So how much are you getting if you go for just trying to find out what is f? So we will get f square is equal to 1,20,000 upon 4 4s are 16 into 3, right? 16 times 3. So how much do you get, children, when you go to simplify this and you take the under root? So f is equal to under root of this value. So 12 into 10 power 4 upon 4 square into 3. 3 ones are 3 fours are. So how much is it getting simplified to? Yes. How much is the frequency that you're getting?
25.
Yeah,
50 hertz, sir.
50 hertz. So 50 hertz. We will get the answer as 50 hertz when you go for simplification. Okay. So the answer is 50 hertz. Option B is the answer. So simplify it and you get the answer as 50 hertz. So here again, from the root, simplify it and get the final answer. Okay. All the simplification, I expect you guys to do it. Okay. I'm showing it for few sums so that you will get the hang of it, but then you will have to do this real time. All right. So that you can save time. So this is how you approach this question. To find out the resistance for when it's connected to a DC source, and then when it is replaced by an AC source, you find out what is the relation with impedance, and then use the formula, substitute. Inductive reactance is again 2 pi FL. We use that, rearranged, extracted frequency, again rearranged, took under root, and found out the answer as 50 hertz. So that is how we found out the answer as 50 hertz for this particular question. The source frequency is 50 hertz. All right. I hope now this question is clear how to approach these models or these kind of questions. Okay. So again, these are important aspects. That's the reason I'm stressing on different aspects of questions so that you have an idea. Okay. Coming to the last model, and then we'll move on to the next chapter. Okay. So the last question, last but not the least. So moving on to the next type. Okay. Next question. We'll see the next question. Yeah. 12 ohms resistor. Okay. 12 ohm resistor and 0.21 Henry. Okay. 0.21 Henry inductor are connected in series to an AC source. Okay, to an AC source operating at 20 volts and 20 volts, 50 cycles. 50 cycles per second. Okay, CPS. And the question is the phase angle between the current and the source voltage is. and source voltage is what is the phase angle between current and source voltage. Options are option A 30 degrees, option B 40 degrees, option C 80 degrees, option D 90 degrees. So these are the options. Okay. So here you have a resistor and basically an inductor, right? So again, we try to represent this question also diagrammatically. So you have a resistor, then you have an inductor. So both of them are connected to an AC source. That's it. In series, they are connected to an AC source. Simple. Okay. I'm writing the values also. So this is 12, 12 ohms, and this is 0.21 Henry. Okay. Both are there. And you have the voltage also. Your AC voltage is 20, right? Yeah, 20 volts, and frequency is 50 hertz. Okay. Why I am saying 50 hertz? Cycles per second. Cycles per second is nothing but frequency only. Okay. The number of cycles per second. Fine. That's it. So this is the figure. So we have now converted the question into a diagram. Now try to extract the particular information based on what is being asked. So they're asking you what is the phase angle. Whenever you have a question as electrical circuit and they're asking you phase angle, you will have to find out what is the relation for the phase angle based on the given data. Okay, you have an inductor and you have a resistor. So whenever they ask you phase angle, it is given by the relation tan phi, right? So tan phi is equal to it here. It is inductive reactance. It's ratio of reactance and resistance. Okay, that's it. Tan phi is equal to XL upon R. So we use this particular relationship. Suppose instead of inductor, you have a capacitor along with resistor. In that case, what would you do? It is the ratio of inductive capacitance upon resistance and the resistance. So it is XC upon R in that case. Okay, like that it gets modified. So now you go and you try to substitute the data and simplify. What is the formula for XL? You guys know it is omega L upon R, where omega is 2 pi F. So 2 pi FL upon R. Okay. Substitute everything and then go for a simplification. Okay. So 2 pi FL. So 2 into 3.14 into frequency is 50. L is 0.21 upon R is 12. Okay. So this is all the data that you have. So finally, you simplify all this, children, you will get tan phi is equal to 5.49. Okay, 5.49 pi. Okay, three values I'm giving. So tan phi is equal to 5.495. So what is phi? Then phi is equal to tan inverse of that value, which is 80 degrees. Tan inverse of 5.495, which is 80 degrees. So like this, you will calculate. Now here, the angle is different. And because you don't have access, to Clark's table, so you need not worry. You will be getting known value of the trigonometric ratios. Okay. So suppose here instead of 5.495, suppose my answer is say tan phi is equal to root 3. Then what is phi, children? Tan inverse of root 3. What is tan inverse of root 3? For this, you will be knowing the angles. You don't need a Clark's table for that. Anybody? Is it 30 degrees, 60 degrees, 45, or 0 degrees or 90 degrees? Yeah, correct. It is 60 degrees, right? So again, if it is tan phi is equal to 1 by root 3, it becomes 60 degrees, it becomes 30 degrees, right? So tan phi is equal to 1. In that case, phi is 45. So like this, known ratios only you will get, right? Because you don't have access to Clark's table. All right. Yeah. So that is how you need to approach these type of questions. Okay. So here for you, the formula is important. How you substitute and simplify, and then you get the final answer. Okay. So with this, we will wind up with alternating current. We have seen all different models of questions that can come. Graphical questions also may come. That also you will have to be prepared. Okay, wherein they give you a graph and they try to ask the uh, question based on the graph. Okay, that is for RMS value. I think that also we saw one question in the last session. So where you have an RMS voltage or RMS current, there is a graph given, and they try to ask you what is the corresponding values of peak current from the given graph. Yeah, that is easy to calculate. Whenever you have RMS value, you can find out peak value. Whenever you have peak value, you can also find out RMS value, right? So that is another model where questions can be asked. That's it. So with this, we come to the end of alternating current, and now we'll move on to a new chapter where again different types of questions can be asked. Okay, so we are moving on to that chapter, which is having an highest weightage. Okay, so we look at that chapter now. All right. Yeah. Let me take a fresh page. This chapter plays an important role. It comes under the branch called optics. Okay, so under optics, you have ray optics. You also have wave optics. So there are two different categories of branches under optics, so from where many questions are generally asked. So today we are going to see ray optics. That is the topic for us. Okay. So when I say ray optics, what comes to your mind? Anybody? Have you heard about optics or have you had information about this before in your lower classes? Definitely in grade 10, you would have come across it, isn't it? So can anybody give me a small introduction before we jump into the concepts of this chapter? What is optics according to you? Yeah. Any volunteers? In your own terms, you can tell me, in your own words, you can tell me. What is this branch in physics which is called as optics, particularly ray optics?
I think it deals with light and its properties, sir.
Yeah, that's correct. It deals with light and its properties. Yeah, you're right, absolutely right. Whenever we say ray optics, when I say ray has something to do with light, right? I'm not talking about the underwater, the ocean creature. That's the sea creature, which is also a ray. Not that ray. Here, this ray is particularly, it's totally different. It is something to do with light rays. Okay, so when you have, I hope you guys would have seen a laser, right? So laser is a classic source of light which gives you a monochromatic beam, a beam of a single wavelength, and you can see it is pointed towards a particular target. You can easily find its path also. The path is also quite straight, and that is how light rays travel real time. You can see morning sun rays. That is also visible, especially when you have suspended particles in the atmosphere. The rays of the sun become quite visible, right? So that's how they travel. The property of light travel in a straight line or a straight path, we call it as actually in a propagation of light. Okay, from that is the basic idea. So always light would like to travel in a straight path. Now, why do you think so? Why should light always travel straight? Why not? It can bend and travel. It can take a right turn, then it can take a left turn, or it can make a roundabout and then reach its target. Why not? Why should it always travel straight? What is so special about light ray? Why should it travel straight? Anybody? Why can't it, bend, bounce, and then, you know, touch an obstacle or a target? Why should light rays travel straight? Haven't you guys wondered about it? Yeah? Always light rays, they try to cover they try to take the shortest path. Okay? They don't take the longest path. Given 2 points A and B, when light ray is incident at point A and it wants to reach its point B, it would always take the shortest path. Why does it take the shortest path? Because light rays appearing from a point source are different. So it depends on from what medium it is traveling on, how it is traveling. Okay, why it travels straight is because light is usually having a dual property. It is having a particle nature also. It is also having a wave nature. Okay, so therefore it prefers to travel the smallest distance between any two given points, and therefore its trajectory is usually straight. That means the path that it takes is usually straight. So we have the concept of something called as diffraction of light. So we will be learning that. Okay, so that's basically the idea. Second aspect is, however, based on the wavelength also, we can try to distinguish the paths that light rays would take to travel. So usually when it is traveling from one medium to another, then it would tend to bend a little. But if it is going to be the same medium, then it travels straight. It is not getting deflected, or it is not going to bend visibly. This the idea. Okay. So now we will, with this basic, we will jump into the chapter. Here, we have different concepts. We have concepts of reflection. We also have concepts of refraction. Okay, reflection. I think you guys know what is reflection. Okay, so first idea is to try to understand what is reflection. Reflection occurs when light ray is going to bend. You know, get reflected. Okay, from within the same medium. Bending in the sense, basically, it is bouncing back. Okay, bouncing back in the same medium. So for this, it would encounter a shiny surface such as a mirror, or you can also take an aluminium foil and you try to make it incident with a light source. You can see light source get reflected, or it is because of its shiny surface, light rays falling on it, tend to bounce back. So that phenomenon of bouncing back of light into the same medium when it encounters a shiny or a reflective surface, you call that phenomenon as reflection of light. So that's the basic idea of reflection. So here, if you're going to draw the light rays, they will reflect. So you would draw them, they will reflect. So this property of bouncing back of light when it falls on a shiny surface, or when it is incident on a shiny or a reflective surface, such as a plane mirror, you call it as reflection. Okay, this is one concept. The second concept is called refraction of light. Okay, that is the second one. What is refraction? How is it different from reflection? Anybody? How is
From one medium to
yeah
another.
yeah one medium to another? That's correct. So how can light ray travel from one medium to another? How is it possible? That means the medium should allow light to pass through, or the light to propagate through, right? So such mediums would allow light to refract or pass through them. For example, we have so many, real life objects which allow light to pass through them. Originally in literature to distinguish between the real world and fictional, virtual or idealized worlds. I'll just come back to this. Distinguish between actors and the characters they portray. Yeah. So refraction is when typically light is going to bend as it passes from one medium to another. Okay. That medium has to be transparent, no doubt, which should allow light to pass through it. So transparent objects, transparent material such as glass is going to allow light ray to pass through it. You have lenses which can also allow light to pass through them. Lens is also typically made up of glass. Okay. So again, glass, and certain lenses are made up of other high quality materials. Quartz crystals are there. Yeah, and you have also expensive stuff like diamond, many other crystals. Okay, so to name a few, you have ruby, you have topaz. Now they all allow light to pass through them. Okay, so then what happens to light as it passes from one medium to another medium? Say first it is trying to pass from air. Say this medium on the top is air. The medium at the bottom of this blue line, let me call that is water. Okay, water is also allows light to pass through it. So when light is entering, say from air, okay, so this is a point of interface. It is trying to enter water. Now what I do is I'm going to draw a special line, a special, imaginary surface or imaginary line. This line is called the normal. Now normal is basically an imaginary line that is perpendicular to the surface of the interface between both the media where the light ray is incident on. Okay. So when light ray is entering from air into water, it would bend towards the normal. Why it is bending towards the normal? Because air is rarer medium and water is called denser medium. Now, what do you mean by rarer and what do you mean by denser? These are again two different concepts. Rarer is basically the lighter medium. Optically lighter medium is called rarer medium. Okay, where light ray can travel with maximum velocity or maximum speed. You all know the speed of light in air or vacuum, which is 3 into 10 power 8 meters per second. This light ray, when it falls or try to travel into water, the speed is not the same. The speed reduces. Why it reduces? Because the density of the medium is increasing. Air is less denser, but water is more denser, right? You know that the particles or the molecules are quite tightly packed than air. They are not random. So therefore, the speed of light gets affected and then it gets bended. So it would bend towards the normal and then it travels. Okay. This is basically called the concept of refraction, where light ray tries to move from one medium to another medium by bending itself towards or away from the normal. We call that phenomenon as refraction. Okay. So now I've given you a basic idea of what is reflection refraction. We also have something called as diffraction. We also have something called as interference. These are all higher level concepts wherein visualization is definitely required. So what I'm going to do is I'll show you an animation where we can easily try to understand the concepts of reflection, refraction, diffraction, interference. So it's very easy for us to correlate those concepts and try to apply them real time. So let's look at the animation and just pause myself and get the audio ready for animation. Yeah, I'm now sharing the animation video. Just let me know if you guys are able to see it. I've started to stop sharing so that I'll reshare it. Yes, children, I've reshared it. I hope you guys are able to see what is being reshared. Audible?
In this video, my aim is to give you the basic understanding of the terms virtual and real images. It's a slightly long video, but it'll be one of the most interesting ones too. I'm sure you'll enjoy it. What you see on your screen is a mirror. It has this plane and smooth reflecting surface on one side. It's called a plane mirror because its reflecting surface is flat. What other types of mirrors have you seen? Have you seen this type of mirror? Well, you must have seen it on the stand of your bathroom or maybe hung up there on a wall. This is not a plane mirror. Try to move your hands over the surface and you will notice it. This is called spherical mirror, or more precisely, spherical concave mirror. It is curved inwards. It is kept there as we use it mostly when we are shaving. Now, the obvious question that must be coming to your mind is, why do we use concave mirror for shaving instead of a plane mirror? For the answer to this question, you have to wait for our future videos. For now, we will be concentrating on the plane mirror only. So let's consider this plane mirror again. When we stand in front of a mirror, we see an image of ourselves in the mirror. Nothing surprising there. Why are we able to see our image? Yes, it's due to the reflection of light. In fact, it's due to multiple reflections of light rays. How? The light rays from the source are first incident on our body. They bounce off from our body and fall on the surface of the mirror and again gets reflected from there. This reflected light then reaches our eyes and we see our image. So what does this tell us? Yes, this tells us that a light ray can get reflected multiple times. The same thing happens for every other non-luminous object as well. If you remember, my initial goal was to explain what virtual and real images are. Let me ask you a question. This image that you see here, is it a real image or a virtual one? This image is a virtual image. In order to explain what a virtual image is, let's first simplify this image. Let's represent this boy with an arrow pointing up. And here is our plane mirror. You can assume the top of the arrow to be the top of the head of a boy. Now, where is the image of the boy formed? When we see the image in the mirror, it seems to us that the image is formed somewhere behind the mirror. But there is nothing behind the mirror, right? For us, the light rays seem to come from the location present behind the mirror. For instance, consider a few light rays emerging from top of the arrow. All these rays are incident on the mirror and get reflected back. Yes, all the reflected rays will follow the laws of reflection. You see that all the reflected rays are moving away from each other, that is, they are diverging. But we know that the image is formed somewhere behind the mirror. So let me extend these reflected rays backwards and see what happens. We see that they meet at this point behind the mirror. And to us, this is where the top of the image appears to be. When we look at this point, it appears to us that all the light rays are diverging from this point. But in reality, there are no light rays behind the mirror. This being a smooth and shiny surface reflects most of the light back and almost no light reaches behind. But yet, we have the perception that the light rays are coming from the point behind. So we just consider the top of the arrow here. We can do something similar for the remaining points on the object to get the complete image. So we say that the image formed here is virtual, or in other words, not real. You can think of a virtual image as an image which appears to be formed in a position somewhere behind the mirror. But in reality, it isn't there. A virtual image is formed when the light rays diverge after reflection from the mirror. Every plane mirror forms a virtual image. This is the first characteristic of the images formed by plane mirrors. Images formed by plane mirrors are virtual and not real. So what is the real image then, and how are they formed? Let's replace this plane mirror with a spherical concave mirror. Why? It's because real images can be formed by concave mirrors. Let's consider the light rays from the same point of the object incident on the mirror. We see that after reflection, each ray is traveling in a certain direction. Note that here as well, each ray obeys the law of reflection. What difference did you notice here compared to the plane mirror reflection? In the previous case, all the reflected rays were diverging. Yes, here all the reflected rays after reflection are intersecting each other at this point, or we can say that they are converging at this point. And the image of the top of the arrow is formed at this point. And we can do something similar for the remaining points of the object too. We get this image. This is called a real image. It is the image formed when light rays converge after reflection from the surface. One important thing we need to know is that real images formed by concave mirrors are always inverted. We will learn more about this in the future videos. You see that in this case, The image is formed on the same side of the mirror as the object is. Real images are always formed on the same side as that of the object, and light rays do reach this position. When we look at the real image formed by a concave mirror, it also seems to us that the light rays are diverging. But here the rays actually are diverging from a point in front of a mirror. Whereas in the case of a plane mirror, it appears to us that the rays were diverging from the point behind the mirror. So did you understand the difference between a virtual image and a real image? When we look at a virtual image, it appears to us that the light rays are diverging from a point somewhere behind the mirror, but in reality, they aren't, as no light reaches behind the mirror. It's only our perception. And in the case of a real image, the light rays are actually diverging from the point present on the same side of the mirror. In reality, light rays indeed reach this point. Hence, we call it a real image. I mentioned.
So now, I hope you guys have got the idea of what are images and how plane mirrors form images and what are the nature of images that are possible for both concave mirrors and plane mirror. All right. So plane mirror is something that we use or encounter in our daily lives. We all have come across plane mirrors in some or the other point of time in our lives. So when you look at your image in the plane mirror, now clearly they have explained from the point of view of ray optics, you can see that the image tends to form behind the mirror, right? Which is our perception. Okay, we try to have the perception that image is formed somewhere behind the mirror, and hence that image is called as a virtual image. Okay, in reality it is not there, but that is our perception. Now, when you try to move away from a plane mirror, what happens to the image that you see in the mirror? How does it move? Will that move towards you or away from you as you are moving away from the plane mirror?
Away from us, sir.
Exactly. It moves away from you. Suppose you are moving, say, 2 meters away from a plane mirror, your image would also move by 2 meters, but on the opposite side. So therefore, the object distance and the image distance is exactly the same as far as a plane mirror is concerned. This is something very important to be noted. Okay, so the object and image distance is same. Now, what about the magnification of the image as far as the plane mirror is concerned? Now, when you look at yourself in the plane mirror, the mirror would show your reflection as you appear, right? It is not going to make you look bigger or make you look smaller than what you are. It exactly shows how you are. It is your image is basically unbiased. All right. So you just see yourself as you are. That's it. But same thing, if you're going to go and stand before a spherical mirror, you would not get the exact same image of yourself. Why? You would either be enlarged or you would either be diminished. You can also get the same size, but you would get an inverted image. So we will now be discussing these concepts in the next video. Okay, so you will be able to understand that in the next animation. So first and foremost, we understand how images are formed. Second, we are able to distinguish between what is a real image and what is a virtual image. Virtual image is formed behind the mirror, that is our perception, and real images are formed in front of the mirror. Now, a simple example for us to correlate between what is real and what is virtual. When we stand in front of a plane mirror and when we try to get ready, the image that we see is virtual. But what about the images that are captured by our cameras and smartphones? Where would you categorize them? Are they called real or are they called virtual images? The photos that you click using the camera in your smartphones or your DSLRs. Anybody? What are those images called? They are also images at the end of the day. But what kind of images? Is it real or is it virtual? Is my question.
I think they are real images, sir.
They are real images. Okay. Why are they real images?
I don't know why. I just thought they'd be real images, sir.
Okay. But you guessed it absolutely right. It is real. Why we call it real? Real images can be caught on a screen. This is an important criteria for real images. Real images are those which can be caught on a screen, which you can print it and you can get it. That's possible. That's a real image. The images that can't be caught on a screen, okay, which you cannot bring it on a screen or reproduce it on a screen, those images are called virtual images. Are you getting it? So that is virtual. Something which you feel, the perception that is there, that is virtual. Something which is there, which is really formed, that is real. Okay, which is formed in front of the mirror, as far as the concave mirror is concerned. Okay, so the pictures taken by your camera, your lenses, or your smartphones is purely real images. Now, what about the pictures that you see in a cinematic, screen? You're going to a movie theater. On the screen, you're seeing the movie. You're able to see the images. You're able to enjoy it. Now, what is that called? Is that a real image or is that a virtual image?
It's a
Real image.
virtual image, sir.
Yeah. Can you please come again? I think the two of you were talking simultaneously, so I could not understand. Yeah.
Virtual, sir.
Virtual. Okay. Anybody with different answer? Somebody said real also, no? Who is that? Who said it?
Real, sir.
It is real. How will it be virtual? You're able to catch it on a screen, right?
But
So,
it's detected from a source, so I thought.
yeah, of course, it is from a source, no doubt. Okay, and it is the it is made and it has been projected on a screen. You are able to still catch it on a screen. That is a real image. Don't confuse. Okay. Now what? Now have you seen children in sunny days when you're traveling in a car? Say it is very hot. Okay, on a highway. Have you seen when you're in the afternoons? You would have experienced from a far off distance, you can see that there is water. But by the time you go there, the water vanishes. What is this called? Have you observed this in real time? You feel that there is water on the road, but by the time you reach there, the water is not there. What is it called? What is that phenomenon called as?
Waves.
Yeah, waves, not waves. It is
It is
called mirage, right? It is called as mirage. And in Tamil, it is called by another term. I don't know if you guys know it.
Carnal near, sir.
Yes, காணல் நீர் அப்படின்னு சொல்லுவோம். Okay, we tend that what it is there, but it is not there. Okay, so that is what is that image called? The mirage is called. That is, will you categorize that under real or virtual?
virtual.
That is virtual. That is something which is not there. It is our perception that we feel that it is there, okay, or that exists, but in reality it is not. So like this, you can try to categorize between what is so called real and what is so called virtual images. Okay. So with this, you will have a brief idea between the differences of what a real and what a virtual image is. Okay. So then we have something called as ray diagrams, children. So ray diagrams are very important. You guys are well versed with ray diagrams of concave mirrors, convex mirrors. In grade 10, you would have learned, isn't it? So you want me to show you the ray diagrams or you know it? For different positions of the object in front of a concave or a convex mirror, there are different, diagrams that you get, ray diagrams. So you guys have a rough idea about it or you want me to show them? Yeah?
Sure, sir.
Okay, fine. So we will look at that also. Okay, so for ray diagrams also we will look at it. Okay, so that you will have an idea. No doubt you would have learned in your lower classes, but you would have forgotten. So we will look at the ray diagrams also. I'll show it to you. Okay, there are animations where you have a clear perception of. You will have a clear idea of how the ray diagrams are formed real time. Okay, so today we are done. So if I start with the ray diagrams animation, that will go for another 10 minutes. So therefore, 10-15 minutes. So therefore, we will wind up here for today's lecture. The next class, we will look at all the different aspects of the ray diagrams, and then we will solve questions also based on that. Okay, so we will jump into the optics part fully. Okay, now today we had a brief introduction. Then we will look at all the aspects of ray diagrams, so on and so forth. What are the common concepts ahead? We have different numericals also. We will be solving them also from the competitive point of view. All right. So until then, I hope everything is clear. Any doubts in today's lectures? You are free to. You're welcome to ask and get it clarified. Okay. Otherwise, we can wind up. Yeah. Yes, children.
Thank you, sir.
Yeah. Welcome.
Thank you, sir.
Yes, children. Welcome. I'll share the notes also for today. You can go through it.
Thank you, sir.
Yeah. Welcome. Welcome.
Thank you, sir.
Thank you, sir.
Yeah. Yeah. Welcome.